Hello everyone, and welcome to this talk on generative models for classification, LDA and QDA. Today we will look at two classic machine learning methods, linear discriminant analysis and quadratic discriminant analysis. Both are examples of generative models, meaning they try to understand how data from each class is produced and then use that knowledge to classify new samples. Even though their names sound similar, they behave differently because of one key assumption. During this presentation, we will learn what they are, how they work, and how to choose between them in different situations. Let's begin. Here are our goals for this session. The first is to understand what LDA and QDA mean. The second is to learn how they work in practice. And the third is to compare their performance and key characteristics. The fourth is to build an intuitive idea of when to use which model. By the end, you will be able to explain LDA and QDA simply and choose the right one for your data. Let's think about what is classification. Classification means predicting a category or label. For example, we can think, is an email spam or not spam? Is a tumor benign or malignant? Is a picture a cat, a dog, or a bird? We train a model with labeled data so it can draw a boundary between classes. That boundary can be linear or curved, depending on the model. LDA and QDA are two ways to build such classifiers. There are two big families of classification models. The first is discriminate models like logistic regression or SVM. Focuses on the boundary between classes, the model PYX, the probability of the label given the features. The second is generative models like LDA and QDA. This model PXY, the probability of the data given the class. They try to understand how each class data is distributed, then use Bayes' rule to classify new points. So, a discriminative model says, let's draw a line between cats and dogs, while a generative model says, let's learn what cats looks like and what dogs looks like. LDA and QDA all belong to the second family, the generative models. Let's see what is LDA. LDA, or linear discriminant analysis, assumes that each class data follows a Gaussian distribution. All classes share the same covariance matrix. The same spread and shaped. Under this assumption, the decision boundary becomes a linear function of the features. In 2D, that's a straight line. In higher dimensions, that's a flight plane. Because of this, LDA is simple, fast, and stable. It works well when the data is roughly linear and we don't have a huge amount of samples, and then we will use LDA. Let's think about what is QDA. QDA, or called quadratic discriminant analysis, is similar but more flexible. It also assumes Gaussian data, but allows each class to have its own covariance matrix. This means every class can have a different shape or spread in space. This change makes the decision boundary quadratic, so it can curve. QDA can fit more complex patterns, but it also has to estimate more parameters. So it needs more data to perform well. So you can say that in different situations, we may use different models. Uh, it depends on your data set. In short, LDA is simpler and stable. The QDA is flexible, but it needs more data. Uh, for the main difference between LDA and QDA lies in covariance. Um, for LDA, LDA assumes all classes share one covariance matrix, but for QDA, in contrast, QDA allows each class to have its own covariance. Because of that, LDA always gives a linear boundary, while QDA can produce a curved one. This is one difference changes how the model behaves completely. Imagine two groups of points, red and blue. If if both groups are round and similar in spread, a, a straight line LDA separates them well. But if one group is stretched or tilted, a straight line will fail. QDA can bend the boundary to better match the data's shape. So visually, on the left you can see LDA is a straight line that can divide the two groups well. And on the right is a curved line, and it's QDA. So visually, the LDA is straight boundary. The QDA is curved and flexible boundary. Now the Bias-Variance trade-off helps us understand when each model works best. LDA has higher bias, is simple, but lower variance. So the lower variance means that the LDA is more stable. The QDA has lower bias, means that QDA is more flexible, but QDA has higher variance. That means QDA can overfit in sometimes. So if you have limited data or your data is roughly linear, LDA is often safer. If you have lots of data and complex shapes, QDA can model them better. Let's apply. We got four questions. We got four questions. The first question, question A: if the Bayes decision boundary is linear, do we expect LDA or QDA to perform better on the train set or on the test set? When the real boundary is straight, LDA's assumption is exactly correct. On the training set, QDA might fit slightly better because it's flexible, but on the test set, the same flexibility can lead to overfitting. LDA, being simpler, usually performs better on new data. So when the truth is linear, LDA wins. So it's because the LDA is simpler and more reliable. For the question B, if the Bayes decision boundary is nonlinear, do we expect LDA or QDA to perform better on the training set, on the test set? Now LDA now LDA is too simple. It can not capture the curved shape, so it will underfit. QDA, which can create curved boundaries, can adapt better to nonlinear data. If there's enough data, QDA usually gives higher accuracy, but if the dataset is small, QDA's many parameters make it unstable. In that case, LDA might still perform better. So, uh, the first situation is nonlinear and enough data. We're gonna use QDA because in this situation the QDA is better. Uh, and the second situation is nonlinear and small data. Then we will use LDA because in this situation the LDA is safer. Uh, for question C, in general, as the sample size size n increases, do we expect the test prediction accuracy of QDA relative to LDA to improve, decline, or be unchanged, and why? QDA in this for this question, we will say QDA estimates one covariance matrix per class, so it needs a lot of samples to estimate all parameters accurately. When data is small, QDA overfits easily, and LDA using only one covariance works more reliable. As the sample size increases, QDA's estimates improve, and its test accuracy can become better than LDA's. So in short, if we have just few samples, we will use LDA. If we have so many samples, we will use QDA. For the last question, we're gonna say, is it true for this statement? Even if the Bayes decision boundary for a given problem is linear, we will probably achieve a superior test error rate using QDA rather than LDA because QDA is flexible enough to model a linear decision boundary. For the answer, this is false because QDA's extra flexibility adds unnecessary variance when the problem is simple. LDA already fits the linear pattern well with fewer parameters, so in a truly linear case, LDA will usually achieve a lower test error. Let's summarize everything we have learned. LDA and QDA are all generative classifiers based on Gaussian assumptions. LDA assumes the same covariance for all classes, and it has linear boundary. QDA knows different covariance, says it has and QDA has curved boundaries. LDA equals simple, stable, and good for small or linear data, and QDA equals flexible, accurate for nonlinear data, but needs more samples. So, in the first situation, if we got just linear data, we're gonna use LDA. In the second situation, we got nonlinear nonlinear and small data, we're gonna use LDA because LDA is more stable. If we got for a third situation, if we got nonlinear but large data, we're gonna use QDA because in this situation QDA is more accurate. But anyway, we should remember that we should always match our model's complexity to our data structure. Thank you. And that's bring the end of this presentation. We explored how LDA and QDA work and their differences, and when to choose each one. If your data is simple or limited, go with LDA. If it's rich and complex, QDA can capture more detail. Remember, the best model is the one that fits your data, not the most complicated one. Thank you for listening. I hope this helped you clearly understand LDA and QDA. Thank you so much.